6sem-Arm microcontroller and embedded system, Session-4, belonging to Module-4. So let's discuss few aspects here with respect to firmware. What a firmware is, does different design approaches for developing a firmware, and language selection for developing and also designing a firmware. Now, basically, when we talk about a firmware, what exactly a firmware is. So let's take a simple example of a calculator. So calculator, when you look at, has a input unit, which we call it as a hex key or a keypad, and also it is having a LCD module embedded into the product calculator. So there is a program which we call it as a firmware program, which keeps on running continuously. And the job of this firmware is to ensure that once the switch button, that is on button of your calculator is pressed, then the firmware becomes, or firmware will be invoked, or it will be activated. So the set of instruction present in the firmware executes one after the another. Now the overall, we can assume that the application involved here is to read if at all any key is pressed, and if a key is pressed, that the data element, the corresponding data which is pressed, has to be displayed on the output unit. So output is controlled with the help of a input device. So you're controlling some of the variables if it's being used. So that's what literally a firmware is. The job is over here, you have one program inside your embedded product, which happens to be a calculator, and it keeps on running infinite number of times, and the job is to scan if at all any key is pressed, and if that key is pressed, it has to be displayed on the corresponding LCD screen which is available in your calculator. That's your simplest example of the use of firmware. Now when you look at the screen, you have one more firmware which happens to be highlighted. Call this as a BIOS for your desktop computer. Desktop computer firmware, normally we call it as a firmware. We call it as a BIOS. BIOS stands for Basic Input and Output System. And here the use of this BIOS is essential. Even if your system doesn't have operating system, no problem, but BIOS indeed is essential. So BIOS has different objectives. One of the aim of the BIOS is to load your operating system, and this operating system gets loaded at the later stage. Initially, whenever you turn on the system, this BIOS program gets run. And one first application, what this BIOS does is it will check whether any of the peripherals connected to your motherboard belonging to your desktop PC, are they working fine, are they in good condition. Assume that you have essential components required for working with a desktop PC, happens to be a keyboard, a mouse, and a monitor. Assume all are interfaced to a motherboard, and you turn on the system. As soon as you switch on the system, firmware gets executed, which is nothing but a BIOS, and you cannot monitor this. If you want this screen to be prompted, you need to enter the key delete. So upon pressing delete, you will get this screen popped up, and this has various features. You can change the date, you can change the time, you can change the clock frequency, and also the BIOS boot up sequence could also be changed. So initially, by boot up sequence, more priority will be given to hard disk, followed by DVD drive, and floppy disk if it is connected to, so on. Suppose if you want to install a operating system, if you want to reinstall operating system, then one thing what you can do is you can place your DVD drive with operator system installed in it. You can use a DVD drive, and DVD CD or DVD you can insert into the DVD drive, and boot sequence you give highest priority to the drive. So in that case, it will not the booting sequence will commence from the DVD drive. So automatically operating system will be highlighted because it is put in your DVD drive. okay, and you can start installing it. Okay, so I repeat, the main intention over here for your BIOS, which is a firmware, is to ensure that check whether the connected systems like the peripherals, input devices as well as output devices which is connected to the motherboard are working fine, or are they in good situation. Suppose if all the connected peripherals are working fine, then it will next load the operating system. So these are the two essential job which your firmware does, or which your BIOS does. And this is the earlier days. BIOS used to come up with a ROM. This was a ROM IC which was also embedded in your motherboard, and it was available, and the content present in this will be, it cannot be written, it cannot be changed by the users. It is read, for read applications it is read only, and the content available over here is also permanent, you cannot delete it. Hope that is clear. And these are some of the points which you can address, but this is not there in the syllabus. This is for the BIOS. If you are using a BIOS firmware, then this is the situation arises. So it is addressed that BIOS, when it has been initiated, so what happens initially, it will check whether the processor has any faults, and next it will check any peripherals attached to it, does it have any fault. So if everything is working fine, then only it will load the operating system. Fine. This is one more example. If you want to upload or burn a firmware onto a controller, then this is one best practice which you can afford to do. If I'm not wrong, many have worked on IoT applications. In IoT applications, you might have come across IC named as ESP8266. ESP8266 happens to be a Wi-Fi module, and the use of this module is to, you can ensure that it works as a router in the sense, forward the information from one unit to another unit. Now over here, if you want to place data onto the cloud, then you can use this module, and the data would be present in the Arduino, or yeah, you can have a data stuffed in the Arduino, which means you can connect some input devices, grab the sensor values. After that, you can transfer those sensor values using Wi-Fi module onto the cloud. So for that, this is essential. So if that application needs to be implemented, then definitely you require a firmware to be dumped onto this IC. So when you purchase this IC ESP8266 online, so the firmware will not be dumped in it. So you have to dump the piece of code which you call it as a firmware into this. So this is actually the connection, the way to dump the firmware into a ESP8266. Those students who have already done it, you can just ignore the slide, and there is a software known as ESP8266 flasher. This happens to be an application app, and this is when you double click on this app, it shows you a front panel wherein selection of COM port, everything will be visualized here, and also you can select the firmware which you want to load it onto this IC. Now the content of firmware, how it looks for your ESP8266, I'll just demonstrate. I'll not tell you what exactly it is doing, but let's look at the content. And this is actually your code. This was the piece of code which I was talking about, the firmware content. So the file, firmware file had .extension.bin file. It was a binary file, and to access the binary file you require an online binary reader. I had made use of a online binary reader, and I was able to grab this content. So this is a binary file itself, so hex value you have everywhere, and this does something. Now the one thing what I can address is the simplest thing what it does is, as soon as you turn on your ESP8266, it is going to blink, saying that the hardware unit, ESP8266 unit, is in a working state. Just to address whether the ESP8266 module is in working state, you will get a LED, green LED blinking. So this program piece of code, when you put it onto the controller, then the LED will blink, indicating that the every hardware present in that ESP8266 is working fine. And also they have various methods. Reason why we upload firmware is to check the AT commands when you are using Wi-Fi module. That is, when you transfer a data AT from the Arduino, you should get a response back to the Arduino okay from the module unit, Wi-Fi module unit. So if AT commands are working good, then only you can proceed a particular application. If you want to build, then you can proceed with. So this is just for verifying whether your device is in good condition. You can always have a firmware dumped in it, and you can test whether the AT commands are working or not. Okay, so these are few things which you can try if you are free enough with, or if you are having ESP8266 module and Arduino, you can try out with this experiment. Okay, so this is actually your syllabus. So as addressed, embedded firmware happens to be responsible for controlling the various peripherals. You can take a simple example of a calculator itself. So various peripherals over here happens to be a input unit, which is a keypad, and an output unit, which is a LCD. So by changing the keys, as soon as you press a key, that is when you give an input, output is also changed. So here we say that controlling the various peripherals indicates output is modified. So output is controlled with the help of an input, and also it responds as soon as you press a key. So you press a key, and if it takes a longer time to display that message on the screen, then your product is not good enough, so you can optimize it. Okay, so that's what you have. So it is basically used for controlling the various peripherals. So this is not generic definition or use of firmware. It is different for different embedded products. And we literally call the firmware as brain of an embedded system. Always we call it as a brain because this is a piece of program which is gonna drive your components attached to the embedded product. So if this piece of code is not available, then the embedded product is having hardware, but it doesn't do anything to make it more intelligent. To make the system more intelligent, definitely a firmware needs to be embedded into your system, and this is one-time process. It is one-time process. Whenever a manufacturer comes up with the product, they will put this firmware piece of code into the hardware, and they will release the product. Now there is one more case which we have seen previous slide. I just addressed you, ESP8266, wherein the product is already released onto the market, and once the product is sold, then you can put the firmware, the required firmware with some different versions also can be embedded onto your product at a later stage. So that's what the third point suggests. Then you have firmware is actually the piece of code which keeps on running infinite number of times till there is a hardware breakdown. Only under hardware breakdown, if the device is completely hanged, then only the firmware will be stopped from running. And most of the embedded products, the firmware would be put onto the ROM. It will be stored in your ROM permanently, and at any cost it cannot be erased by any users. But there is a method to modify the firmware versions you can change with the help of operating systems, which probably we will discuss in the later class. Then again, the final point over here is to ensure the proper selection of the programming languages which you need to select for designing your firmwares. Since your firmware, if you want to write a piece of code for your particular hardware, definitely you should understand the hardware first. The architecture of the controller needs to be learned first. Only then you can write a optimized program. And the programming language you can afford to use, you can either use a high level language like C, C++ or Java, or even you can select a programming language assembly level programming language could also be made use. So there is the choice of the language which you are selecting for writing the firmware application program varies, because it is sometimes what happens is when you write a program, firmware program, microprocessor language or assembly language might give you the better result. In some scenario, high level language program may give you the better result. So the choice of programming language selection makes huge difference if you want to develop a very efficient product. Okay. Mm, and the embedded firmware development process. So here what we will discuss is, if you want to develop a firmware, then what is the plan which you need to look at. So initially, from the firmware, first we write we split this firmware complex application into modular into modules. Something like we can come up with a flowchart, and we can define the various tasks for a particular modules sequentially. Once the modules are identified for a particular embedded product, when you're writing a firmware, later you can write a individual program for a particular modules. So this is model developing. So selection of model implies a block diagram. Okay, it represents the pictorial representation, the flow, the manner in which you are supposed to write the program. Before writing a program, you are supposed to come up with a block diagram. Then the modules present in the block diagram needs to be identified. Each module has to be programmed separately. So after one module gets completed, or when the module gets completed, executed first, then the second module will be switched over. This way you can write the program. So that's the firmware development process. So you have a flow chart followed by the program. So you can think of flow chart to some extent, you can think as if this is your abstract class, wherein what and all components you require for developing your application needs to be highlighted here, and its implementation part is written in a concrete class. So think as if this is your abstract class, this would be your concrete class. And this is the different firmware design approaches. I've already indicated you have two firmware design approaches. One is super loop based firmware design approach, which is normally called also as conventional procedure based firmware design. And second one is operating system based firmware design. So the first method, which is conventional procedure based firmware design. In conventional procedure firmware based design, you're not gonna use any operating system. And why would you use this kind of a firmware? This kind of a firmware will be advantageous when you don't expect the response time from the peripherals to be very quick. So you can use, for example, you can consider the calculator part itself. So as soon as you press a key, I want the output to be displayed, but even if there is a fraction of second, it doesn't make a huge difference. And your firmware which has been put in this small embedded product is not very high-end code, probably a code with 100 to 200 lines that particular application suits for this. And this program has to be continuously run again and again. It depends how many modules you are using. Suppose if your system is having many modules, one module after another gets executed sequentially. So it follows the procedural programming concept. In procedural programming concept, suppose if you are having n tasks, task 1 gets executed first, followed by task 2, then task 3, so on it continues till you arrive at task n. Once task n gets completed, then you go back to task 1, and this process repeats again and again. So that's your task based or procedure programming concepts. Hope this is fine. But one disadvantage of the super loop approach is, suppose if there are multiple interrupts triggering your embedded product, then this program may the program what you write may not be able to sufficiently schedule which to which interrupt device you need to provide the service. So that is one disadvantage which you have when you are using super loop based module. Okay, and this is the execution flow of a super loop based module. So what basically you are supposed to do first step is to configure the pins. Suppose if you are using a controller, and some of the ports of the controller should be connected to an input device, and some ports may be connected to the output device. So this the first job over here is to set the directional flag, whether the pins are configured as an output or pins are configured as an input. Consider an example of calculator itself. So definitely the lines ports available in some of the ports pins may have to be connected, which you will be connecting it to the hex key or keypad needs to be set as the input, and the keys or the pins which you're connecting it to the LCD screen has to be made output, which is you're sending information to the output peripheral, whereas for a keypad it is you're reading the data from the keypad onto the microcontroller. So configuring your keys, configuring your pins are essential. After that, designing, you require an initialization system to be called. In initialization system, what you do is the clock frequency can be set here. Okay, and then you come up with the task. You start with first task, go to the next second task, third task if present, repeat till you arrive at the end task, then go back again and execute the first task. You are not going back to one, because configuring is done at the first instance itself. If you remember Arduino code, you remember inside void setup we expect the instruction written inside void setup to be run once, because there we will be configuring, and in the setup loop we will address which pin we will be using and what is its mode, is it input or is it output. Similarly, the communication speed, like the baud rate, we will address inside setup, and the task definitions you put always on a loop. So here loop, void loop, its equivalent syntax in embedded C code is while of 1. While of 1 implies while true always repeat the instructions inside the while loop, and it is equal to void loop in your Arduino programming language. So all the task needs to be put inside loop, and the configuration part and initialization part has to be addressed in the setup loop. As a programmer, you can find this would be the kind of a abstract program which looks like for your super loop based firmware. So you will be having configurations, then you will be having initialization. This two things could be considered as for your LPC 1768 Cortex M3 controller. You think as if these two are your startup file and system files. So you require those where the clock, either it might be related to the clock speed, you define the clock speed, it might be related to configuring your pins. All are addressed first, then you write inside the while the program you write. Probably you think as a first stepper motor program effects. So you will be having a port initialization, you'll be having its direction set. Also you will set you will call the libraries like startup init and system init. Also you will invoke other libraries like system LPC and startup LPC. So then you write the main piece of code will be put inside while statement, and that will be running again and again. Okay, and here you have you are not using operating system. So one of the disadvantage of this method already addressed happens to be when there are multiple interrupts connected to the embedded product, which for which interrupt you need to give highest priority, is not defined, and it is difficult. And also when you expect the result to be the response time from the microcontroller unit to your interrupt to be very fast, then you cannot afford to use super loop based. Super loop based approach cannot be used as a firmware for developing application under real-time scenarios. For real-time application or developing real-time embedded products, you cannot afford to use super loop programs or super loop based approach program. So always you may have to use either a general purpose operating system, or you may have to go with a real-time operating system. Those are the valid operating systems which you can use. Above those operating system, you can write a firmware. So that's the second point what we have. Embedded operating system based approach. Now this approach at any cost will not use operating system. That's the first point. So here whenever you want to develop an application, you will be writing an application on above the operating system. And you can think as if writing a firmware program for your general purpose, for your operating system on the operating system. Can think as if your RT operating systems, the firmware will be developed above the operating system. So for this, operating system is also essential, and also the firmware is also essential for designing. And you can get more security using this technique. And you have various operating systems. So if you remember Windows, Unix, Linux available. If you want to write a firmware for your desktop machine, or if you're writing a firmware for your embedded product, again you have a general purpose output or operating system. General purpose operating system for embedded product is also available, and this is the name of the operating system, which is general purpose operating system exclusively made for your embedded product. And what are the products? Your handheld devices. It can be a PDA, portable PDA, personal digital assistants. You can use even your tablet PC, all mobile devices where you expect the response time to be very fast. So you can always use operating system on and all are operating system based firmwares. Okay. And for developing an application, any application related to a firmware, you have a operating system along with, and you're supposed to write a firmware application with the help of operating system. For doing this, the two essential things which you require is the operating system supported APIs. So API stands for application peripheral interfaces, and in Windows environment you have massive amount of APIs available, Win32 APIs, and all APIs provides services for your peripherals. For example, you might have come across Windows Movie Maker, which is an app, and that app in turn is used for playing videos. Also you can use the same app to play audio signals or audio information or audio objects. Similarly, you have Window Media Player, again one more app that again is used for playing the video and audio too. So that's about APIs. So this APIs are already available. Suppose if you want to write a firmware level program for a particular video unit or audio unit, you can pull this API from the Win32, and there itself you can modify it. And one thing what you require is API, and one more software what you require when you're working on a firmware application, OS based, happens to be a device driver. So why device driver is required? So device driver provides, if at all you have a hardware unit, and if that hardware unit present in your embedded product needs to be connected or interfaced with the help of an operating system. You might have a operating system like Windows 8.1 embedded for embedded applications. In that case, if I want to drive a device, if I want a peripheral to be enabled with the help of operating system, then you require a device driver software. And device driver software could be always installed from the manufacturer's websites. You can select which device its version you have in your system, and if you want that to be updated, you can always go to the manufacturer's website and you can pick the relevant driver essential for your application. And also you need to select which platform you're working on. Is it a Windows a platform you're working on, or other platforms? So generally this device driver is used for communicating your board peripherals, the components present in your board, with the operating system, because operating system provides you a good GUI. Windows GUI is better than DOS GUI. DOS, what we used to do is we used to type some commands on the command prompt, and thereby we were able to communicate with the hardware present in the processor. Similarly, if you want to communicate with the peripherals using operating systems, you have a various apps, APIs as addressed, which provides kind of application. And from this application, if you want the peripherals to get responded, then definitely you require device drivers. So that's a thing about APIs, device drivers. So that's for communicating purpose. Definitely operating system, if it needs to be communicated with your peripherals, you require a device driver as well as APIs to make your system look more attractive. And one more based approach, you have operating system, general purpose operating system based firmware you can add, or also you can use real-time operating system based firmware can also be designed. And this is used in those embedded system where time factor is a critical. You can think as if you have a anti-brake locking system wherein the time is a critical factor. As soon as you press a button in that system, the seat belt has to be triggered. So their time is one thing which is critical. So in that case, you can use RTOS, real-time operating system, can be used, which when you have multiple number of interrupts, which is having scheduling and multitasking environment embedded in it, or services provided in it, using these services it can smoothly operate your system. Okay, so some of the embedded systems which uses real-time operating systems are PSOS, POSIX operating system which you call. Then you have VxWorks, ThreadX, Embedded Linux. These are various examples of real-time operating systems used in some of the real-time embedded systems. Okay, so I repeat, real-time embedded system uses RTOS as the operating system, and this operating system would be used when you demand speed, when you want a good response from the embedded unit. You can think as if it's your handheld devices itself, like a mobile app where when you swipe the window will vanish, or the next window will be scrolled on. So those things and all can be done with the help of this kind of a real-time operating systems. So smartphone could be one of the examples which could be addressed here.